Hi everyone. So, the second in our Euler Educate series, I hope you're all well and that you're looking forward to hearing from Kasper Pawlowski, who'll be telling us all about how to integrate ERC-4626 Vault with the Ethereum Vault Connector. As always, if you have any questions, do pop them down in the chat or the comment section below and we'll come to them for the Q&A portion of Kasper's talk. All that remains for me to say is that I'll hand you over to Kasper. So over to you, Kasper. Thank you.
Hi, Don. Thank you for the introduction. Do you hear me, by the way?
Yes.
Perfect. Okay. Okay, so let's start. Hello, everyone. Welcome to our second workshop of the series Euler Encode Educate. My name is Kasper Pawlowski. I am a Solidity developer at Euler Labs. I am not an Ethereum OG. I joined the space about 3 years ago. In my previous life, I used to work as an aerospace engineer. I was mostly involved in safety critical systems development. But about 3 years ago, I decided to join more exciting field. And this is how I ended up here in the blockchain space. Let me share my screen and we can begin the workshop. Okay, perfect. So the title of today's workshop is how to integrate ERC-4626 vaults with the Ethereum Vault Connector. If you attended our previous workshop, you probably already know what Ethereum Vault Connector is. However, I have a small recap for you. So the Ethereum Vault Connector, the EVC for short, is a brainchild of Euler Labs team. The EVC is an open source project that was designed to connect ERC-4626 and other types of vaults to enable their use as collateral for one another. What we would like the EVC to become is this kind of foundational layer for developers to build their own lending products, stable coins, yield aggregators, and other products on top. Before we dive any further into the EVC, maybe let's first talk about the ERC-4626 standard. So what is it? Well, it's a tokenized vault standard that was proposed about 2 years ago. It was created to optimize and unify technical parameters of yield-bearing vaults, and since then it was adopted by many projects. And by the way, we at Euler, we are also planning to use ERC-4626 for our V2 version. It provides a standard API for vaults that represent shares of a single underlying ERC20 token. And basically what it offers is this functionality for depositing, withdrawing tokens, reading balances, nothing more. What's interesting about this standard is the fact that it does not specify how the yield is generated. In fact, it might not get generated at all, and you will quickly find out about it during this workshop. What you need to know is that traditionally it was not possible for vaults to have borrowing functionality. So to generate yield, vaults would always need to deposit their assets into other smart contracts according to their strategy, right? And this is because vaults are standalone entities and they need some kind of communication or coordination layer in order to be able to generate yield by lending out their assets. And thanks to the EVC on which vaults may rely, they can now enable the borrowing functionality, which was not possible before. Okay, cool. So let's take a look at the bigger picture to better understand today's task. So the primary purpose of the EVC is to connect vaults and mediate between them. As you can see at the diagram, the EVC can be surrounded by a constellation of vaults. Each of those vaults can have different underlying assets, can accept any number of other vaults as collateral. They can have different borrowing terms. They can be governed by different rules. To allow borrowing, each vault chooses a set of vaults that it accepts as collateral. And if a vault does not accept any collaterals, then no borrowing is allowed. Ultimately, a vault in its purest form does not need to provide borrowing functionality, as I already mentioned. And it can be a simple vault that only allows depositing and withdrawing assets. But as long as it's correctly integrated with the EVC, it can be accepted as a suitable collateral by other vaults that have borrowing functionality. So for example, you can see that vault number 3 is a simple non-borrowable vault because it does not accept any collateral assets. And but still, it can be used by vault number 1 and 4 as a suitable collateral, right? To illustrate the process of vaults mediation, let's consider a straightforward example. So let's imagine that you want to borrow WETH from vault number 1. In order to do that, you need some deposits in vault number 2 or vault number 3. Let's imagine that you already deposited something into any of those vaults or into both of them. The first thing that you need to do is you need to notify the EVC which vaults you are intending to use as a collateral. Again, you can select only one or both of them. Then you need to notify the EVC from which vault you are intending to borrow assets. You choose vault number 1, and we call this function enabling a controller. And this is very significant because from that point on, the controller, which is vault number 1, controls those assets that you enabled as collateral. And that control is granted because the debt is taken from the liability vault. And in order for that vault to be able to seize assets in case of liquidation, that control is needed, right? After we enable controller, if a user wants to perform any action that may potentially affect account solvency, so for example, if you borrow from vault number 1 or if you try to withdraw your collateral, the EVC will be responsible for calling the controller vault to determine whether the action is allowed or it should be blocked to prevent account insolvency. So with that setup, what can we achieve? Well, we can have multiple lending protocols that are built on top of the EVC in parallel that can be interoperable, and this should allow for easy bootstrapping of new products. We can have isolated vaults that accept collateral that is sitting in another isolated vault or another product that is built on top of the EVC. Or maybe this is a niche use case, but you can be a single lender and you can lend out on your own terms, right? So imagine that you have a bunch of WETH and you just create a vault for yourself. You can accept any other vault deposit as a collateral, so you don't need to convince people to come to you and deposit anything into your contract. The collateral might be sitting anywhere, and it is up to you to say that this collateral is okay and that one is not. And this way you can be competitive with the terms and the rates, and we hope that you can easily find a counterparty that may be willing to borrow from you. So what is the EVC ultimately? Note that we've made a full circle because we started with that question at the beginning, and now we are asking it again. So ultimately, you can think of the EVC as a special purpose multi-call contract, which additionally provides caller authentication and maintains execution context, which may be relied on by external smart contracts to enforce accounts and vaults' healthy state. And that's a quite complex definition, so let's break it down. I mean multi-call contract because you can perform any operations on many operations on many different vaults. in a single EVC call. In fact, you can call any external smart contract because the EVC does not have any restrictions when it comes to that. The EVC authenticates the caller, and it either allows or disallows an operation. The account address on behalf of which the operation is being performed is stored in the execution context of the EVC, and that information can be retrieved by a vault during the execution. Also, vaults may schedule account and vault status checks to be deferred and performed at the end of the batch of operations. Thanks to that, you can transiently violate the rules and then fix the situation before the checks are performed. So for example, you can flash loan, you can easily rebalance your positions, or you can set up a leveraged position easily thanks to that. However, in order to do that properly, the EVC needs to keep track of users' enabled controller and collateral vaults. This is something that I mentioned here at the beginning. Okay, cool. So what we are going to do today is we will try to integrate the Open Zeppelin implementation of the ERC-4626 vault with the EVC. The only thing that we will do today is the EVC integration. Thanks to that, other borrowable vaults will be able to use our vault as a collateral. And it will work in the very same way as vault number 1 from the diagram used vault number 3 as a collateral. And the type of vault which we will create in this process we call collateral only vault here at Euler. It also means that our vault will not be earning any yield because it will neither allow its asset to be borrowed, nor it will deposit them in other smart contracts to generate yield. However, I will ask you to implement the borrowing functionality for this vault as an assignment task. I encourage you to go to this link and clone the repo, and so that you can follow with me, or you can just watch whatever I am doing here, and you can implement everything later. Before we jump into the code editor, I would like to provide you with solution outline so that it's easier to follow later on. So to understand the solution, the first thing that we need to realize is the fact that vaults may be called directly or indirectly via the EVC. I think that it was already mentioned in the previous workshop, but let me reiterate that so it's clear. So we need to allow the vaults to be called directly so that they are still ERC-4626 compliant, right? So for example, you may want to call the deposit function directly on a vault, and that should be allowed. But at the same time, we want to use all the goodness that the EVC provides. And for that, oftentimes, we need to call the vault through the EVC. So from the implementation standpoint, there are two reasons why this is important. So the first reason is the message sender. We need to properly handle the message sender in both cases. And we will do that by overriding the message sender function that Open Zeppelin implementation uses. I will show you the details later on. But the second reason is the fact that when the vault is being called directly, such functionalities as batching, sub-accounts, operators, checks, deferrals, all that stuff that I mentioned before, it cannot be used. And why is that? Well, because we are not in the EVC context, the EVC doesn't know that any operation is being performed on the vault, right? And moreover, depending on the implementation, we may face some reentrancy issues. So because of that, we encourage the integrators to use a special call through EVC modifier that we will implement today. And that modifier will imitate as if the vault were always called through the EVC using the callback pattern. And by doing this, we will ensure, predictable behavior of the vault, and we will be able to use other EVC features that I mentioned. Then we will implement the with checks modifier to ensure that relevant checks are always being scheduled after the operation. And finally, we will implement 3 simple functions from the iVault interface that are required for the EVC compatibility. And we will override existing ERC-4626 Vault and ERC-20 shares token functions also in order for those functions to be compatible with the EVC. Yeah, I think that this is it here. Let's get to coding. Let me share my code editor. Okay, perfect. So what I have here is this Euler Encode workshop repo cloned, and I also installed dependencies here. We will work on the workshop vault.sol file that can be found here in source workshop 2 workshop vault sol. This is a simple contract that I created for this workshop. It looks like that because I wanted to be able to compile even in this state. It should all work. But let me explain what I am doing here. So let me close this as well, and let me maybe make it larger. Okay, so let me explain what I'm doing here. So first of all, I am importing the ERC-4626 implementation from OpenZeppelin. And then I add a bunch of interfaces, right? The first one is the EVC interface that we will need to interact with the EVC. The second one is the iVault interface that I already mentioned. And this is this interface. It contains those 3 functions that we will need to implement in order for this vault to be compatible. And I have also some iWorkshop interface, and this is assignment related. So I will explain that later on. I just put those functions here so everything compiles. So what do we do? Well, first of all, we need to inherit from ERC-4626 and iVault. We also need to provide an EVC handle, which is an immutable, and we will pass the EVC address here in the constructor, and we will define this immutable, right? But we also need to instantiate the contracts. We need to instantiate the ERC-4626 with the underlying asset contract, and also the ERC-20 shares token by providing name and symbol. And this is our constructor. So the first thing that we need to do is we need to override that message sender function, right? The one that I mentioned. If you go to the ERC-4626 contract, you can see that wherever OpenZeppelin needs to refer to the message sender, they use this function. So if we override it, and that function gets called, we will always provide this implementation with the relevant caller, right? So this function, it lives here in the context file, in the context contract from which ERC-20 contract inherits. Let me copy this. Let me put it here. Let me add override. And okay, so as I mentioned, we need to figure out if we are being called by the EVC or directly, right? So let's write message sender equals address EVC. If we are being called directly, the only thing that we need to do, we just need to return message sender here, as that function used to do in its default version. However, if we are called through the EVC, we need to take the account address on behalf of which given operation is being performed from the EVC context. In order to do that, we use EVC get current on behalf of account. It takes an input parameter, but I will just pass 0 here, and that 0 is for optimization purposes. When you are solving the coding assignment, you will need to actually the questionnaire assignment that I will explain later. You will need to figure out why I passed 0 here and what has to be passed in other circumstances. But for now, let me put 0. And let me simply return the caller address that I got from the EVC context, right? Or we can, to look better, we can name it on behalf of account, which formally is the case. Okay, so this is our message sender function. The next thing that we need to do, as I already explained during the presentation, is we need to implement this call through EVC modifier. It doesn't take any parameters. And once again, what do we need to do here? Well, we need to check if we are being called through the EVC already. And if we are being called through the EVC, we simply do nothing. We just execute the body of this function, and that's it. However, if we are not being called through the EVC, we want to imitate as if we were called. So in order to do that, we will call to the EVC, and then EVC will call us back with the same payload that we are being called right now. So in order to do that, we will use the call function. If you go to the IEVC interface and you look for function call, you can see that this function calls into a target contract as per data encoded. So basically what we want to do is we want to pass our own address, address of the vault as a target contract. We want to pass the message sender as the address of an account on behalf of which this operation will be performed. We don't want to pass any value. And for data, well, basically we want to call the same function, but using the EVC. So let me do it here. We are passing our own address. We are passing message sender as on behalf of account. We are passing 0 as value because we are not sending any ETH, and we use message data. And by doing this, we will call EVC, and then the EVC will call us back with whatever was provided here. The only complication here is that we need to slightly abuse the solidity modifier pattern, right? Because we need to return from here. We don't want to execute the function body anymore. So we need to take whatever that function returns, and this is the result of the function being called. And we need to provide assembly one-liner here. So we want to take this result and return it. But we also need to remember about stripping the first 32 bytes in order to provide appropriate encoding. This is it. This is our call through EVC modifier. The next thing that we need to do, as already explained, is we need to implement this simple with checks modifier, and this one will take account address. And what do we want to do here? Well, basically we want to execute whatever operation is being executed, right? We don't bother what kind of operation that is. And here we want to check if the account provided is being 0. And by doing this, we will signal to the EVC that we only need to schedule the vault status check and that the account status check is not needed. But if we pass a meaningful address, we want to require both of them, account and vault status check, using the account address provided. Cool. So that's it for this modifier. So the next step is we need to implement those 3 functions. The first one, disable controller, is a function that is called by a user in order for this contract to release itself from being a controller. For us, at the moment, it will be very simple because we can simply unconditionally call disable controller, and we can just take whatever is returned from the message sender function here. However, if this vault were borrowable, what we would need to do here is we would need to check if that user has fully repaid their loan. And this is critical operation because if the controller disables itself, it means that it will no longer control the account. And if the loan was not repaid, it would mean that the user would be able to simply walk away with their loan, because that controller would no longer have control over the collaterals that are enabled, right? So user could simply take the money and run away. Also, when you are implementing the borrowing functionality for this vault as an assignment task, please pay attention to that, right? It should not be unconditional. You need to check if the debt was fully repaid. The second function is a function that is called by the EVC whenever we, after the batch, whenever we request the account status check, this one here. And this function should always be called by the EVC, and it should only be called when checks are in progress. There is a flag in the EVC context, which indicates that checks are in progress, and only when they are in progress, this function can be called. Because remember that anyone can call anything on the EVC, so that the requirement that it's the EVC calling is not enough for us. So the first condition is that message sender is address EVC. And the second condition is our checks in progress flag must be true. Okay, cool. And why do we need this function? Well, in our case, it is not really needed because this function gets only called on the vault that user enabled as a controller and when somebody scheduled the account status check, right? Because our vault is non-borrowable, there is no borrowing functionality here. It means that there is no need for anyone to enable this vault as a controller. However, when you implement the borrowing functionality, then somebody will enable this vault as a controller. And what has to happen here is you need to implement some custom logic evaluating the account health. So basically what you need to do here is you need to check if with whatever the account has already borrowed, considering the collaterals, if this account is healthy or not. If it's healthy, you simply return the magic value that is required by the EVC, and it's the selector of this function. If the account is not healthy, you simply revert. And this bit really shows the EVC flexibility, because you can do whatever you like here. You can call whatever oracle you like. You can hardcode prices. You can implement any risk management strategy you like. And it should all happen right here, right? You can call some external smart contracts in order to figure out if this account is healthy. But basically, you have freedom to implement whatever you like here. Okay, that's done. And now we have the check vault status. And for that one, it's very similar. The only difference is that the EVC expects the selector of this function to be returned when this vault is healthy. And what we are doing here is we are figuring out, evaluating if the vault is healthy, right? So what can be implemented here is, for example, supply caps, borrow caps, rate limiters, all the other stuff that let you figure out if the vault is in a healthy state or something bad happened, and this operation should be disallowed. It may happen that you need an access to an initial snapshot of the state of the vault, right? So, for example, you need to compare what's the total supply right now versus what was it like at the beginning. In order to do that, you can implement some snapshotting logic right here. Just remember to take the snapshot once, and then you can use it. You can store that snapshot in the storage of the contract. And then when this hook gets called, you can simply compare the current state versus the initial state, make a decision if the vault is in a healthy state or not. And you need to remember that you need to clear that snapshot, right? So that when this modifier is executed in another transaction, the snapshot is taken once again, right? But for our simple vault, this is enough. You're free to implement any strategy here. Okay, so these are those three functions that need to be implemented for the vault in order to be compatible with the EVC. So the last step is to override the existing functions of the ERC-4626 and the ERC-20 shares token functions, right? So in order to do that, we can go to the ERC-4626 implementation and to the interface, and we can find those functions that need overriding. It's a deposit function, that's for sure. Then mint function, which is very similar. Then we have the withdraw function. And finally, redeem. And also we need to go to the ERC-20 and we need to take the transfer functions, because users can transfer shares of the vault between one another, right? So those also need to be overridden. Important note here is that there is an approve function on the ERC-20, right? But in fact, we don't need to do anything with that function because it simply takes message sender, right? And this is the function that we've already overridden. We don't need to do anything else here. So we have those 6 functions, and what do we need to do? Well, all of them are public. We can make them virtual so that when you inherit from this vault, you can once again override it. All of them are overridden. And now what we need to do is we need to simply use that call through modifier that we've implemented, right? If you were in need to use a non-reentrant modifier, if you wanted your vault to be reentrancy protected, which is not needed for the Open Zeppelin ERC-4626 vault. However, if you, due to some reason, you needed that protection, you need to put non-reentrant right here after the call through EVC, because otherwise you would encounter a reentrancy. But we don't need it here. But what we need is this with checks modifier. And now, what do we need to pass to this modifier? Well, in case of deposit, when user deposits anything into a vault, it cannot negatively affect their solvency, right? So we don't really need to check the account status check. The only thing that we would like to check here is the vault status check, so that, for example, a supply cap can be implemented here. So we would schedule this hook to be called, but there is no need to check the account health per se. So we pass address 0. And we need to do the very same thing for the mint function because they are almost equivalent. This one takes assets, that one takes shares, but they work in a very, very similar manner. Then we need to do something with the withdraw and redeem functions. Both of them take owner parameter where you specify from which account the assets are being withdrawn or redeemed. So here, considering that the owner's health can be negatively affected, you need to pass the owner address to this modifier in order for the account status check to be scheduled for owner. And you do the same for the redeem function. Then we have a transfer function. So transfer means that we are transferring shares from somebody to somebody else, right? We are transferring share in case of a transfer function, we are transferring shares from the message sender, which health can be negatively affected here. And in case of the transfer from, we are transferring the shares from the from address, right? As for the to address, we don't need to do anything because from the perspective of the to address, it's like regular deposit. And in case of a deposit function, we did not schedule any check for this account, for the receiver account, right? So this is it. And now we need to do something with the implementation. It is very simple because considering that we've already overridden the message sender function, the only thing that you need to do here is you need to call the original implementation of the deposit function, right? You simply write assets receiver, and that's it. And you need to do the same for all of those functions, in fact, right? So you put mint and shares instead of assets. Then we have withdraw, we have shares, we have receiver and owner. For redeem, we have shares. Then we have transfer to value, and we don't need that. And for transfer from, we simply need from to value, and we need to use transfer from function. And this is it. Our vault right now is EVC compatible, which means that it can be used by other vaults as a collateral vault. We can try to compile it. let me first call forge FNT so it looks better. Probably, yeah, it will not work. There is a typo in here. There is some issues. Okay, so it seems that for the transfer function, we need to specify what we are overriding. And we need to do the same for the transfer from. Yeah, so now it compiled just with 2 warnings, and those warnings we get because we didn't use the inputs to this function. Because we simply returned the function selector, right? But when you are evaluating the account health, you will need to use both the account address and the list of collateral that this account uses as collaterals at the moment, so that you can fetch that account's collaterals balances, you can price them, and you can figure out if this account is healthy or not. But for now, we don't need to do this. We can run forge test. And as you can see, almost all the tests are passing except for 2, and both of those tests, they are assignment related, right? So the first one is a basic flow test. Basically, what it does is it tries to, deposit something into a vault, and it tries to borrow and repay. And of course, it doesn't work because our vault does not have a borrowing functionality. And the second one checks if the interest is being accrued, right? In fact, this is something that is optional to be implemented. You can, the assignment requires you only to provide borrowing functionality without interest accrual. But if you want to dive deeper, you can also implement interest accrual here. So I think that we are done here. Our vault works. So let me explain the assignment tasks. So if you go to the README file of this repo, there is an assignment section, and basically it explains how everything should be done. I mean, how it should be submitted. What we ask you to do is to fork this repository to solve the assignments, and then create a PR trying to merge into this repo, and this is how we will assess all the solutions, right? But also it explains what the assignments are. And as you can see, the first assignment for today is a questionnaire. And I will simply put some questions here in this file that we worked in. And I will ask you to answer those questions inline in that file. And also we have a coding assignment, which will require you to also work on this vault that we use today and implement borrowing functionality. There is some more information here in the iWorkshop Vault file that I mentioned at the beginning. And it tells you what to do, basically. So it asks you to implement those 4 functions: borrow, repay, pull debt to transfer debt from one user to another, and simple liquidate function, which only takes violator and collateral address. You can implement, very simple liquidation strategy in order to close unhealthy position. And also there is some tips. So it also tells you not to forget that some other functions need to be overridden. And there is also some optional stuff that, if you're interested in this, in those topics, you can also do something optional. As I said, interest accrual, you can integrate any kind of oracle in that account status, check account status hook and liquidate function. You can implement a circuit breaker in the account, in the vault status check hook. It may be EIP 7265 inspired. You can familiarize yourself with this concept. You can add compatibility for RWAs, but all of that stuff is optional. So if you like this, you can dive into it. If not, only this is strictly required for this assignment. Okay, so let me stop sharing my screen here and go back to the presentation. Yeah, so the assignments, as I already explained, there are two of them, questionnaire and coding assignment. The questionnaire will be judged first come, first served basis. We will reward probably 10 best answers, and there is a prize pool of $500. And the coding assignment, this one will be judged together with workshop 3 coding assignment, right? So we will judge the submissions, we will select the best ones, and 5 best submissions will be rewarded, and there is a prize pool of $2,000. Here are the resources that might be helpful. In fact, the only one that you will need is the evc.wtf, because from here you will find links both to the EVC repo and the playground repo. The EVC repo is where the EVC lives, right? But the playground repo is like a sandbox/examples repo where you can just go and look up some implementation patterns and try things out. So it might be very helpful for your coding assignments, but also for the questionnaire, I believe. To answer the questionnaire questions, probably whatever I told you today during that workshop will be enough. But you can also dive into the documentation that you can find under this evc.wtf link. We also have a bug bounty. So while working on this, if you spot any bug, feel free to report it. You may get rewarded for that. There is a $100,000 bug bounty program that we launched together with Encode. You can find all the details here under this link. It's also evc.wtf website, so it will be easy for you to find it later on. Yeah, and I think that this is it. Thank you for your attention, and see you at workshop 3 that will happen on Thursday and will be held by Doug. This is all from me for today. I'll be happy to answer any questions that you may have. Okay, yeah, as I told you, those questions are not available yet. I will add them shortly just after this workshop, and I will push everything in a few minutes. Oh, there is a question from Mohammed. What are the software architecture type adapted for this project application? So, well, in fact, this is something of our own. So basically, we were trying out things. We were proposing, trying out, breaking, adapting, and this is what we ended up with. In fact, there is no reference to anything else that we know of that is out there in the DeFi space currently. Yeah, whatever I develop today, I will also push that into this repository. So let me turn my screen, by the way. Yeah, so I will push everything I've done today. So it's just easy for you to kickstart with the coding assignment. Question from Rob: does the solution need to use any other parts of Euler protocol, or can be any Vault example? So in fact, Euler v1 is not useful here at all because it was a monolithic lending protocol. We are building something entirely new, and that is not live yet. So yes, you should be using Vault examples only, because Euler v2 does not exist as of now. Okay, another question from Mohammed, what are the developing norms, ISO, etc, and the standards that you recommend to follow while the life cycle development process? Well, the approach basically differs in our industry because it's very nascent. So we are still trying to figure out what are the best, life cycle development processes. But personally, what I really like, what some people find quite outdated, is this waterfall pattern that I learned when I was working as an aerospace engineer. So whole aerospace industry basically relies on this pattern, and this is something that works. This is something that was proven over the years. So I would say that for smart contracts, which I also consider to be software critical software, I think that this is the best way to do things. I see no more questions, so I think that we can end here. Okay, guys, thank you very much for your attention, and see you Thursday.
Thank you so much, Kasper, and thank you everyone for coming. So yeah, as you mentioned, on Thursday we'll have Doug back to take us through the unique features of the Ethereum Vault Connector, which I'm sure we're all really looking forward to.
Yeah, Doug will go into details regarding the account and vault status check deferrals. He will mention something about the sub accounts, about operators, which are whole another feature set of the EVC that you get out of the box if you integrate with it.
Amazing.
Okay, cool. Thank you. See you soon. Bye bye.
Thank you, everyone. Bye.